Today's talk would be about building scalable, asynchronous, event-driven applications. I know there are a lot of words out there. As you get along, I hope each word of that sentence makes sense for you. Okay, let's get started with the agenda here. So we'll start with event-driven microservices, the basic intro and stats, and then we'll move on to the hybrid event-driven architectures, and then we move on to the data loss aspect of it. Within the data loss, basically we'll cover the enterprise reconciliation, how you basically manage this data loss at that scale. And the next step would be managing the scalability aspect of it. Within that, there's a couple of topics I wanted to cover. How does that actually impact the databases and exception handling? And then we will move on to the last one, which is multi-tenant systems. At any point in your work or life, right? So you basically, whatever the tasks you do is all dependent on the decisions that you have taken in the previous part of your life, okay? The same thing applies in the software as well. So I wanted to touch upon these decisions, how you actually shape them, and how the eventual decisions, also get impacted as we move on to the session. Just a quick intro, sorry, I forgot myself about myself is I'm working as a staff software engineer in Walmart Payments. So I work in the area of fintech and payments team. Okay, so let's move on to the basic introduction. This is a very classic image, as you can see here. So you start with basically a monolith, and you basically move on to dividing into microservices. So this is a very simplistic view, but as you move from the left to right, there is a lot of things that would be happening in a typical microservices architecture. So I'm not covering that part, but this is the end state of what you move from a monolith to a microservice. And then we basically have different modes of communicating between the two microservices. One is synchronous. Generally, it's an API, how you talk to two microservices. And the second one is, the asynchronous way. So this is the main focus of this talk. Okay, as you can see here, the asynchronous most likely would be based on a message broker. So you send this data to a message broker, and eventually, you expect a consumer to consume that, and that's how two microservices talk to each other. So another complex level, if you're doing most things like not just reading the messages and maybe sending the messages, right? So you may have a lot of responsibility, okay? Then this is where it might look something like this, like you also have an APIs, you might have consumers basically that are reading from message brokers, and at the same time you may also have bad jobs. Now this is a consolidated view. You can have maybe different modules or projects, whatever you define, managing each of this, because if you have to scale an API or consumer, the things are different, right? So you cannot put everything into one repo, but a lot of systems or teams might start that way, but eventually they basically slice it down into them. This is within a team, again, within one team microservice, again, you can split them across, okay? So the requirements are different, but at a base level, we wanted to cover that a platform has a more responsibility added compared to a typical microservice and a very basic one. So having said that, these are some of the key stats we can see regarding the microservices. You might have listening the buzzword of microservice. So you have 20%, even less than 20% are actually matured in managing the event-driven architecture systems, right? And we have less than 40% are understanding the real value of event-driven. And mostly event-driven, they come into the categorization of using for mainly for data sharing, IoT, and generally the application integration is the common use case. Okay, the data systems which we might be using, that's generally comes under a different category. So that is where the talk actually focuses on combining the microservices, which is generally a software engineering aspect, combining with a data engineering, basically, which is a data streaming. Okay. So the next step is maybe taking a one step ahead is managing the hybrid event-driven systems. Now in the previous slide, we have seen that you either choose a sync API or you basically choose an async route, which is basically a, using a message broker, right? But it's very rare that you have only one in the system. So this is where the hybrid EDMs come into picture. So as you can see here, this is a typical integration in a hybrid EDM. Okay, the left one, which is the source, message broker, and the target, mostly this is the same thing what we have done the previous, right? However, as you get the data towards the target, and that is where the consumer is actually processing the data. So it's not just you get the data and you process it right away. However, you might have to integrate with multiple systems here. Now, one of the system could be the third-party API, where that third party can be another team in your organization, or it can be outside your organization. It doesn't matter. But because if you see that the decision we already made is a microservice split up, and obviously we have to take a decision now to see how you manage the data across these two. Okay. So now that's a third party API. Now, a lot of times, as I mentioned again, you are a platform team here, so you have more added responsibility. So there are few things which you may have to integrate with respect to your history as well. Now, generally the history is you do your work, and then you basically send the data to a data lake. And then you also have to make sure that the history stats are also integrated into your core application. That's where the arrow is coming from. That could be a asynchronous aggregated data. Okay, and the next further level is generally you have the AI models that will be feeding the data from the data lake, right? Now again, the inference, that's what the last arrow is basically, right? Most likely, again, this is a very oversimplified version, but still, this is the general architecture how you have in a typical microservice, sync and async. So you wanted to have an inference, and you want to do that either real time, or if not, in a near real time as well. So either way works. So that's the first step I wanted to cover, like very fundamental how a typical microservice architecture would be and what are the challenges and the basic stats, right? Next, we'll move on to the data loss aspect. Okay. So most of the common are like, so as you can see here, how can you miss an event? That's how I want to cover in this, right? In my view, so I've been working in the data streams, so data streaming applications for the last 10 years, and I've been in the microservices for the last 5 years. So what I think is a monolith is more like a marriage. Basically, everything is intact. It may be slow, but it gets the job done very, very well. But when you go to a microservice architecture, it's like a live-in relationship. You basically work together. You want to move fast. Yes, it is possible. But if you don't have an agreement, in that case, children may be spoiling. In the organization, data is the one that gets impacted. So there's a lot of places where you actually have lost control of the data, because a team is sending data from one system to other system, and they say that, okay, I send the data and I'm done with this, right? And the other team basically says, okay, I got the data. As long as I processed all the data, I got it, I'm good. However, there is one case which I would like to explain here is the lost ownership. So when you talk in terms of two teams talking, with respect to the data sharing aspect, they might win between the teams, but the organization is impacted if there is no agreement on who owns the data and how you do the reconciliation between different systems in an org. So take, for example, this example. As you can see, the same example for the typical microservice architecture. You have a source sending 8 events here. The target is receiving 8 events, and a classic database storage, 8 events. So everything looks very clean here, right? Until you understood that they're actually supposed to send 10 events. So you never know that basically there are 10 are supposed to come to my system, right? However, if you are a team that basically are at the end of the pipeline or maybe facing to the customer, the first tickets and all comes to your team basically, right? And now you have to understand, okay, I got the ticket now, Jira ticket, whatever it could be, right? And now you're worried about, okay, an event is missing, where is it basically in the entire pipeline? Now you have to dig through that and make sure that you're also understanding, right? So generally, I suggest to my team members that you need to know your neighbors when you're working in a system, but especially if you're in a microservice system, you need to have that known to a 2 level. At least you need to know who are their upstream systems as well, not just your upstream and their upstream. That would help you to understand a bit more about the system and how the data is coming in. This is a basic use case. Now coming to another one. As you can see here, the source got 10 events, and now you have 10 events. They send it to the broker, and now you actually target is receiving 9 events in this case. Eventually, the database ended up with 8 events. Now, there can be multiple reasons for this. One could be, most common could be the Kafka broker failures. Now, I know Kafka is very resilient, and some of the issues can be related to hardware, and there could be insufficient replication. You are very optimistic about your problems, but eventually they occur. So that could be the case. And at the same time, knowledge gap. Now, knowledge gap is where you are actually, the team is learning and you're not fully confident of the settings that you put for the Kafka, so you end up with losing the data. The second type of issue, if you can see here, is the target, the consumer itself, right? That is the most common. So in a typical Kafka integration or any message broker, the consumer is the most complex compared to the producer, because generally the producer, they send the message and most of the times they expect the data to be there in the broker. But the consumer is the most critical part, because they are responsible now to gather the data and make sure they are 100% efficient. So if there is any issue with the consumer, that's where you lose the data. Okay, so this is one of the cases. Now, the third case is more or less the one that we talked about a couple of slides back, as you can see, right? Now, just with 2 systems, generally you have 4 combinations. I try to think always in that way. Like if you have 2 people talking to each other, one is right, other is wrong. The reverse, both are right, both are wrong. So you have only 4 cases. Now, you're adding another 2 layers here, basically. So you can expect more data loss happening unless you are having a complete control of what is going on in each of the system. However, it is very difficult, because if you see the first 2 slides, right, microservices have the capability to get you delivered the results faster. That is coming as a result of teams taking their own decisions faster and using their own tech stack, and they have their own maturity levels. So, and if you're working in a bigger organizations, you have very limited control of how you can take your decisions. You can definitely move faster. However, you have to always think in terms of how can I make my features safe and deliver them, even if the other teams are not delivering faster. So that's one challenge you always have. So there is always a more chance of data loss here. Now, the next step is, so we have seen how data can be lost, right? There are multiple ways. These are some of the classic ways where the data can be lost. Now, what can you do as a team member, and how can you basically make sure that this is taken at the enterprise level, okay, not at the team level? So this is one of the architecture where you can use from a end-to-end reconciliation point of view. Okay. Now, the color coding here is, as you can see, the green is mostly the existing one, still the same. Okay. So you have source and the target, and now I actually added another source here, because generally that's how the systems are set up. So you have two sources sending the data to the target, right? Now that's the primary pipeline. You just don't need to worry too much about that. However, now we are trying to understand what events are missed. Okay, so the goal is basically to have an integration layer and actually the storage layer to, like, both the systems need to be sending the data. Now, who owns this part? Obviously, the target system. Okay, that's what because if you see in the previous slides, right, the whole requirement is that you are the end system and you have more responsibility to take care that every event is tracked properly. Okay. However, you have to work with the source team, right? And at the same time, if you put any reconciliation checks within the target, you may not be able to 100% tackle it, because as you have seen in the previous cases, the data loss is happening outside your system. However, you have that added responsibility to make sure that the data is not lost. So we add an integration layer here, okay, and generally we have multiple ways of managing the data. The easiest would be a message broker again here, where you send the data to a Kafka broker and let it stream into a Snowflake database. You can use the Snowpipe Streaming here, okay. And why we have to add another layers of integration here is, as I mentioned, each system is matured differently, and they may not have the access of the data to be sent to Kafka in real time. So some can be able to send maybe after 1 hour, some can be sent at the end of the day, right? You have to make sure that the integration layer is supportive of all of these integrations. Now, one more very important part here is the last part, which is, where you're getting the data from multiple systems and you are actually doing a reconciliation. You can treat that as a very basic joins. However, which data needs to be sent and at which time drives this entire architecture. So as you can see here, at the end of the day, when you're joining two systems, you need to align on the identifiers you wanted to use, that because you're reconciling. So I have 10 events on the left-hand side, and I'm getting 9 events now. You need to make sure both you systems are actually talking in terms of the same identifiers. Now, the source system can do many things again here, right? Because once they receive the data, they have their own pipeline managing, right? But as long as they have the identifiers, that is the time you expect them to send the data to the integration layer. So that is very important, because you don't want to wait very late in the game from the source system to make sure they send the data. I have seen some cases where they don't want to send in real time, but they wanted to send at the later part of time. But by the time the damage is already done, because they receive the data is lost in their pipeline, and now basically you cannot send the data. So the target will never even know that there was an event that is missed already. So that's one of the issue there. And the last one is, once you have that, you can do a reverse reconciliation as well. Like you have the baseline of, okay, the source is sending 100, now I got 90. That's one way, right? And you also can see that, okay, most likely, because there may be some reasons where you received some data and something might have happened at a later point of time in the upstream system. If you want to do that, you can actually enhance the basic reconciliation with a reverse reconciliation as well. And then the remaining things are the classic, like an insights, alerts. You can actually put the alerts. The left arrow basically is the auto healing. Now, auto healing is a tricky subject, because you are identifying some of the categories of the errors, and you are making a decision that you can auto heal and you can retry. But again, if you see, the arrow is basically going to your source system, not your target system. So you have to have a good agreement there, or SLA, so that they basically are aligned with that and they are retrying that at the source level, not at the target level. Okay. So going to the one level down here, so this is the same view, but double clicking on that, so you can see the source events there, and we also have a target events. So generally, the important part is the timeline, the time boundaries which you actually read from these two systems, and then you basically dedupe, and then we'll touch upon dedupe in the next few slides. So and then you have a dedupe system basically, and you join the system, and then you actually provide the analysis here. Okay. So what are the metrics I'm trying to get here? Okay. So these are the high-level metrics you can actually get based on the system which you develop right now. The first one is the master reconciliation and the reverse reconciliation, which we just talked about. At the same time, you also have a customized SLA per source. As I mentioned, not every system is capable of sending the data in real time. So depending on how they send, you can actually customize this, and your reconciliation can be elastic in nature, and you can, but the max time I generally would take is 24 hours. Okay, so that's up to how you wanted your reconciliation to happen. And the next one is the lifecycle tracker. Now, what we have seen here is generally a very simple version. As I mentioned, you got the data, you just persist in its database, right? But it's very common to have multiple lifecycle phases where you wanted to track on each system that, hey, I want a phase 1, 2, 3, 4, and the final phase is the 5th phase, right? Till now, we talked about the 5th phase being the final one. But if you want to drill down this reconciliation, you also can have a capability of sending an event after each life cycle, and you can still do the reconciliation, which means that you basically have 100 events. Your first life cycle event got actually 95. Maybe by the time you go to the bar, right, every level you actually can drill down and make sure that you have the reconciliation, and that's where you can trace the event as well. The last one, of course, is the high level, because these are all aggregated metrics. You can actually have the impact option, which is generally the revenue and the trust factor as well. Okay, so these are the bird's eye view. And obviously, you just don't want to mention that, hey, I got a 95 events now, because the focus is making sure that you capture the data. So you have to dig down into double clicking on that to make sure that you have the missed events and the reasons why it is mismatched. Okay, so you can define these mismatches, and this is the base of the auto heal regarding why it is missed. So the last one, as we can see, right, is depending on the life cycle you choose, you can also say where the data is stuck. Okay. So that's a high-level details about the data loss. So we covered the basics of that, how you can actually lose the data, and even what we can do and what we can get out of this enterprise reconciliation. So the next topic is the scalability topic. So as we talked before, if you have worked in the microservices, you might understand that are asynchronous EDS the only way to scale? Now, this is a broader statement. I understand you might have a very different trade-offs, but in general, if you have two microservices and you want to scale, you cannot keep on adding these API calls at that scale. So most of the teams generally rely on event-based systems. So this is a good, a relevant statement in that combination. And the answer would be yes. Okay. So having said that, now let's take this particular option, and then now let's see how you actually can dig into the scalability aspects at multiple phases. Okay. Again, we're talking about a data streaming aspect here. We moved from microservices to a phase where we understood that data streaming is the one for you to manage scalability. And then from there, we are talking about how you can actually scale within the, with consumers. Okay. So this is one of the ways generally how a typical consumer is set up. Okay, I think this is, most of you might have already known that. As you can see that one block is one partition in a typical Kafka setup. Okay, and then what you do is read, process, and persist in the database. Okay, now normally once you read the data, you don't split up the individual parts apart. Okay, you just continue processing this entire event within one of your worker nodes. However, if you wanted to have a case where you want to slice it down at that level as well, there is possibility for you, which is like, you want to do only the read part and then deserialize, and then basically have a different scaling, at the process way. Okay, so this is how it generally looks. Okay, now this is not always possible with every framework you use. So it again depends on couple of frameworks like which I have used, Spark, basically, where you can actually slice it down individual layers, and then you can actually do. The general use case for this is nowadays you can actually have messages which have maybe 10 events within that each message. Now your inbound layer is not having the same requirements of scalability as how you process, because now you're actually increasing 1:10 ratio, and now you need more resources to basically process that at that layer. And at the same time, sometimes if you wanted to aggregate again, you don't need that many resources, so you can actually do a repartition as well. Now, one thing if you have known into the data engineering is the repartitioning has some kind of a network movement. Okay. However, if you see the entire fundamentals of data engineering combining with microservices, you already lost the data locality concept in streaming. Because if you say take any batch job generally, right, you have a concept of you move the code to the data and basically they work together on that particular node. However, when you work in this setup, the problem is you're already working with a typical maybe a NoSQL database, and it generally works in how an application works, because you bring the data to the code but not the opposite. So that's already, there is a trade-off already there. So that's where the network is already a problem there, but you should be able to leverage that as a trade-off for scalability. So coming to the next part, which is a deduplication. So this is one of my favorite part, because deduplication, you can do the deduplication in a number of ways. You either can use application-based deduplication, or you can use a database. Like if you have a primary key, it automatically takes care of you for the deduplication, right? So when you get the data. However, you need to understand, in theory, the time window is infinite, because the late event can come at any point of time, right? So you always have the restriction of what you can manage. So it is good to have a database taking care of this deduplication. It works, again, but if you wanted to manage that within your system, if you take any of these tutorials on Apache Spark on any streaming applications, you will see that there is a deduplication concept, and you always have to mention the time window, and there is always a restriction that you have to manage your memory settings based on how much data you want to dedupe. Now, yeah, in theory it works, but as you have more and more data and the data is coming at a very later point of time, you may have to rely on the database to manage that. That way your application will be on the lighter side. You don't have too much doing into the application. And then the last part is it also impacts, how, as I mentioned, right, that's where how the typical framework you choose can impact whatever is going on here. The next one is basically the database impact. So generally, when you talk about scaling, you might talk in terms of horizontal scaling and vertical scaling. Okay, because yes, you basically provide more hardware or you provide more nodes. That's how you scale. However, it's not as straightforward as it seems, because especially when you combine apps and databases. Now, apps, yes, you have cloud, you have Kubernetes, so you basically can scale as long as your applications are built properly. Because just because you have a horizontal scaling option, and if you have an inefficient coded algorithms inside, right, you cannot leverage that horizontal scaling there. Right? That's where you have to understand how do you code in such a way that you can actually leverage the scalability aspect of it. For the database, it's not as simple as, I think it's definitely getting better right now compared to the previous times, because all of the databases are managed. However, it is still not pretty simple to basically scale the database in a horizontal way, just like how you do that, from an application point of view. The next one is obviously the in-memory. So the next 3 points, right, like, the in-memory flushes, compactions, and configs, these are specific to the type of database you are dealing with. Once again, if you are in a data engineering stack, yes, you have these analytical databases, or maybe preferably a NoSQL like Cassandra or HBase. If you are a typical application, you have a Postgres, MySQL, right? But here we're talking about streaming in general and database in general. Okay. So in the next slide, so I will touch upon this part, which is what are the different types of stress points in the databases, depending on the type of database. When you are working with the application streaming. So as you can see, most of the times you can see that these are the common stages which the data undergoes in a database. Okay. So the first one, there may be a SQL engine. Again, this is not common across all the databases. Okay. And then because NoSQL, most of the times, the SQL is not 100% compliant. But it's just, you give specific queries which are not relevant to the SQL. And then you also have a commit log. Okay. Now, commit log is where you might have problems with the streaming. Okay. Now, one aspect I want to mention here is, in a typical application scaling, you get the load in a very incremental way. It just doesn't happen immediately. What happens with the streaming applications is there are more chances for the stress points to get elevated in a very short amount of time when you're working at scale in a streaming application. So that is the challenges which we have faced in the past as well, because you can still control how much data you're processing by leveraging the Kafka, the thresholds and all. But again, there's always a chance that your database can be stressed. That's the whole point of this talk here in this database impact. So depending on the type of database, as you can see here, the stress point for, especially for analytical databases, if you are a data engineer, you might understand that there are these small files issue, right? But again, now this small files issue is also being taken care, including the Snowflake, by automatically merging these small files. Okay. But if you take any of these, there are other databases like hybrid databases, which is like ClickHouse, for example, where it works in a combination of both phases, right? Okay. And then yes, there is a merging happening internally, but if you don't know the configs of that merge, okay, you can end up in actually having the database down on that particular node. So that is very important in that aspect. Okay, so you wanted to know slight internals from even from an application point of view, how the merging is happening at the back end, right? On the other side, on the right hand side, as you can see, it might basically go to the disk. That's where the actual files are there, and you also have the flush. If you the flushing is basically, right, if you take any of these go internals to the Cassandra or in NoSQL, most of the times the memory, the data is basically stored in the in-memory and then basically flushed on a continuous basis to the underlying disk. So that is where you might have a control, and that's also the reason why you actually can afford to write the data at that scale and leave it to the Cassandra basically, because that decides when to actually flush it down to the disk. So if you don't manage this properly, this is one of the stress point it might help create. Okay, so this is the aggregated view, as I mentioned. So again, there may be a lot of subparts inside this, but most of the databases come into this part. So you might need to understand how a streaming application can impact your database. So the next part is basically the exception handling. So how you manage exception handling when you're working with a typical microservices architecture. So as we have seen in the past, synchronous, everybody knows about this, an API call. So if there is an exception, you deserialize, validate, and process. And if there is a bad exception, you generally bad data input, you generally give a 4xs. And if there is a system exception, you give a 5xs. This is a classic API response. Now you can translate that knowledge to asynchronous basically, and then see, because if you can think in this way and write a code in this way, that way you can actually move from a normal typical multi-threaded application to basically a multi-node scalable application in a typical streaming application architecture. Okay, so but if you don't do this way of writing code, then I think the migration will be difficult. You might have to rewrite a lot of stuff, but if you can have this thinking, that will be easy for you to migrate as well. So as you can see, the same problems, but this time if you have a bad exception, maybe you might have to persist for analysis. If it is a retriable exception, you might have to republish. Okay, because we'll just quickly talk about republishing, because if you go with any Kafka based, people say, okay, what is the how do you manage exception, right? The common thing is DLQ, dead letter queue. Okay, but it's not a simple solution, because I'll cover those as well. So that's why there are two options here mentioned. So as you can see here, do you have to reprocess and or persist? Okay, which one should you choose? So one of the cases is how easy it is to set up. Obviously, a DLQ is a very simple option because it's already there given by any of your cloud provider. So you can just put it there and bring it back. So it's pretty simple. If you have to put that in a database, you have to think about, especially at a scalable options, you have to think about how do you retrieve the data. Because if you want to put the data in just in any of the NoSQL, again, we are thinking about scalability here. So obviously, your kind of options are NoSQL and analytical databases. So if you have to do that, you have to think about the data models and then see how do you query the data. That's the most decision factor. In Kafka, as I said, the DLQ, you may not be required to do that. Okay, so it's pretty easy for you. And then the visibility aspect, that's what I was mentioning, right? Because visibility is basically a bit complicated in Kafka, because just because it is there in the broker, you cannot query easily. However, you may have to again think about adding a consumer and basically and see that that consumer is again stable to make sure you are understanding this. However, in database, once you think about data model, you're done with this. You can query and you can build dashboards on top of that. Storage aspect, again, most of the times you may have to think in terms of TTL based, because you cannot give a broker beyond 7 days. So that's the max you generally think about, right? But a database has an option, you can actually put it for more time. So you need to think about, can you retry or do you want to retry for how long, and then eventually make sure that after certain retries you basically put it into the database. Hybrid is generally the preferred, as I was mentioning once again, right? So you always have to master how do you think about hybrid options. That's where I think your best profitability comes. The next one is basically the multi-tenant systems. So multi-tenant can be anything. Okay, if you are working on a platform, what I mean by multi-tenant here is you build a system, you build a platform of capabilities. Now you want to replicate that platform maybe to a different market. The underlying functionalities are same, like almost like 80% of them could be the same, and there is always a transition phase where the 20% is still pending, but you cannot leverage the full thing. Okay, it might take time. Sometimes it may be years, basically, where you can leverage the 100% of the platform for a different tenant. Okay, now this is the transition phase we're talking about, especially when you're working with the microservice architecture. So this is one way. Okay, so as you can see, in the first one, you have a source, basically an inbound, and you have a consumer, and you also have an outbound. You basically send the data. Okay, this is a classic microservice with a asynchronous mode. Now let's say, for example, you are bringing in a tenant newly into the system. Now the goal is basically to leverage as much as possible. Now there could be multiple phases, like one source is completely compliant of the features what you have, and they're ready to use the platform as is with just by changing a tenant. In other case, maybe you might have to introduce an adapter basically to make sure that it is compliant. Now, when you design this adapter, it's very important for you to make sure that you think your end goal, which is kind of in a source tenant one, right? Now, it will be surprising for you to understand that once your source or tenant 2 matures, how easy it is to just switch over, because you are already taking care of all of that in the adapter basically, and then you just do a flip, and once it matured, everything is compliant to your platform capabilities. Now again, on the other side of the story, which is like you have the outbound adapter as well. Now there are already clients who are using your services. Now they are already built with a particular SLA and agreement. Now you wanted to again do something right now, because the inbound adapter has something different. So obviously you may have to customize that from an outbound adapter and make sure that you also send the data accordingly to the to that customer, because if you see here, the adapter basically made sure that a different format is compliant with the platform format. Now there was a client who needs a different format, which is from the platform. So you have to again do the reverse of that and introduce an outbound adapter and then basically send it to them. So again, these adapters has to be designed in such a way that keeping your end goal into mind. So with that, I would close the session basically. So just to summarize on that, we talked about multiple points about data loss and scalability. Mostly, as I said, that if you have to summarize everything, microservices, data engineering, and data streaming, and decisions.